All right, everyone, welcome to a new lesson on optimization today. And a lot of you might be happy to know that this is actually our last lesson on optimization. So we've talked a lot in the last couple weeks about optimizing rectangles and square boxes and cost and finding area and perimeter and all that. Um, Today's lesson on optimization is going to be, and this again is our last one on optimization, is going to be on cylinders and optimizing a cylindrical shape. Okay, so obviously you're going to have to upload your work to Google Form again. And just one last plug, I know I've talked about this week and sent out an announcement to you guys. Just know that we have a knowledge check tomorrow. Your knowledge check is just going to be one question from this week's material and one question from last week's material. So when you do your practice worksheet today, the first couple questions are going to be on cylinders, and then under that there's another couple questions that are more review questions from last week, so to help you brush up on it a little bit more. And then I'll also post some practice problems tomorrow that you guys can try before you do your knowledge check. Okay? So this first video, there's going to be two videos today. This first one, actually they're both on cylinders, and they're actually both pretty similar. They're just a little bit different in their wording and what they're asking for, but essentially these two problems are the same thing. The only difference is today you'll have two videos, so maybe it gives you a little bit extra notes to take or a little bit extra time to try and understand it. But let's use this first video for this first problem. It says a cylinder must have a volume of 1,800 cubic inches. Okay? So right away I'm seeing that in the first sentence we have a constraint. Okay, the cylinder must have a volume of 1,800 cubic inches. Okay, it says find the radius of the cylinder so that the surface area is minimized. So it looks like that's our optimization equation, just dealing with surface area. Okay, so just like every other problem, let's draw a picture here. Okay, I'm going to draw a little cylinder and start to label my different variables and my different pieces here. Okay, so I've got this cylinder. Cylinders have circular bases, circular tops. So let's set this up. I have a constraint, and my constraint, the thing that's constraining me, is volume. Okay, it's telling me that it must have a volume of 1,800 cubic inches. Okay, now I have an optimization, or something that I'm trying to optimize, and that's going to be surface area. Okay, it says up here that surface area is minimized. Okay, so a couple things here. We want to write the equation for volume of a cylinder, and if you haven't looked that up yet, the equation for volume of a cylinder is pi r squared h. Okay, so let's just label a few things up here. The radius, the r, stands for the radius at the base of your cylinder, also at the top of your cylinder. So your r is your radius of those circles. Your h is the height of the cylinder. Okay, so if you just think about this volume equation, pi r squared is area of a circle. So you're taking the area of this circle and then multiplying it by height. Okay, so volume is we're filling it up. Okay, and we also have an area equation. So how do we find the surface area of this cylinder? Let's think about this. Well, we can get the surface area of the top and bottom. Those are circles. Area of a circle is pi r squared, and there's two of them, one on the bottom, one on the top. Okay, but now we need the surface area of this wrapping. Think of there's like wrapping paper around this cylindrical piece here. How do we unwrap that and find the area of that whole surface right there? Okay, so I'm going to write plus. Well, if we find the area of that whole surface that's surrounding this cylinder, let's just say there was wrapping paper on here and I ripped it off and I laid it out flat. Okay, so let's take this wrapping paper around the cylinder and let's lay it out flat. This would have been my H. Okay, so this piece right here would represent this circumference. Okay, so what's the equation of circumference of a circle? If you remember from geometry, or if you looked it up, it's 2 pi r. Okay, so the area of this cylindrical surface is going to be 2 pi r times h, And all that together added up is going to be my area. Okay? Now, let's look at this. 2 pi are our constants. R is a variable, R is a variable, H is a variable. Which one looks to be the odd one out? Looks like H is the odd one out. Okay? So our volume is 1800 equals pi r squared, H. And if I write this in terms of H, I can get 1800 over pi r squared, and that's equal to H. Okay, so just like what we've done the last 2 weeks, that allows us to take and plug it into our second equation so that we only have one variable. So I've got 2 pi r squared plus 2 pi r, and my H is going to be 1800 over pi r squared, and that's going to all be equal to area. Remember, my H came from the first equation, okay? By the way, all these cylinder problems, at least the ones that you guys do today, are pretty much going to be the equations, the way you set them up, as far as area and volume, are going to be pretty much the same, okay? When you set it up like this is important that you know when you're multiplying here, you have a pi and an r in the numerator, a pi and an r in the denominator. So if I can take away this pi, take away this pi, I can also take away one of these r's and one of these r's, okay? So if I rewrite this, I've got 2 pi r squared plus, now I can multiply 2 times 1800 is 3600. And now I've got an r in the denominator. Remember, I had r to the first down here, but I'm just going to write that as r to the negative 1 because that's going to help me when I take derivatives. Okay? So far, so good? All right, let's find the critical point, and let's see what our r is so that our surface area is minimized. So let's take the derivative of this. Okay, when you're taking derivatives, please don't be fooled into thinking that pi is a variable. Pi is not a variable. Pi is something we know. It's a constant, okay? So think of 2 pi as your constant. So when I take the derivative of this, I would bring this 2 out front, and it would be 4 pi r minus, because remember I take this out front, so it'd be minus 3600, r to the negative 2, which I'm just going to put in the denominator, r to the positive 2 equals 0. Okay, so that's my derivative. This is my a prime of r. Okay, that's what this is. All right, so similar to what we did with volume yesterday, last couple days, we have to find our variable. We have to find what r is. Okay, so I'm going to say negative 3600 over r squared is equal to, when I bring this over, it's negative 4 pi r. I can multiply both sides by r squared. Okay, so then I have negative 3600 over negative 4 pi, I should say, negative 4 pi equals r to the third. Because remember, we can add our exponents together. Okay. So there's a little bit of canceling we can do here, a little bit of simplifying. So 3600 divided by 4, negative over negative, is going to give me a positive, but that's just going to give me 9 over, but I still have this pi down here, so it'd be 9 over pi equals r to the third. Now remember, we just want r, so I'm going to take the cube root to get rid of that third power. So this ends up being my r. Okay, this first example does not ask for, it does not ask you to like round to the nearest hundredth or thousandth or anything like that. If the problem does do that, then you actually want to get a number value for this. But for this case, it just says find the radius of the cylinder so that the surface area is minimized. This is going to give you a more exact answer, okay? Obviously, if you do this in your calculator, it's going to be a wild decimal, but this is a more exact answer, okay? One quick check just off to the side here, a double prime is going to be equal to 4 pi plus 7200 over r to the third. If you were to get this value and plug it into here, that would still be greater than 0, which means we are at a minimum. So our surface area is minimized. Okay?